Okay, so if you want to find the beta and theta, then you have to go to the code on clause 11.3.6. And as I said, it is not an easy discussion, or it's a long discussion. And look at my screen, please. So there is one page and another page from the code. So guys, what happens here for the purpose of our class today, I will make it short, but I will revisit the same topic or the same clause one more time on Monday. So for now, we have to use 11.3.6.2, and you can see it says the values for special member types. So unless otherwise permitted by 11.3.6.3 and 11.3.6.4, the value of the beta shall be taken as 21%. Please read this one as a percentage, because I want to say, you know what? How much from the DV is 21%, 0.21. And the theta shall be taken as 42 for any of the following member types. Please take your time, read through A and B and C and D and E. What happened is the code is asking you if you are into one of these condition or member types, you can use your beta equal to 21% and theta is 42 degrees. On A, it says slabs and footings, slabs or footings with an overall thickness not greater than 350 millimeters. So if you are designing a slab or a footing, while the thickness of your footing or slab does not exceed 350, it means 150 to 100 to 150. How much is my beta and theta? It is 21% for beta and 42 degrees for theta. Okay? And so again, as I said, this is a long discussion and I will run the discussion in details. So please don't worry. I will run the discussion in details when we design beams. Today, I want to keep things going. So looks like for slabs, and you guys know, anybody built in this class has experience and built any slab more than 350 mil. That is that's a 14-inch slab. I'm not talking about footings, slab. Did anybody build a slab more than 14-inch? Gord?
No, no. The slab should be only either more than 2 inches. Not more than a maximum of 2 inches for the grade slab, grab slab, grade slab. The slab on grade.
So it's 2 inches. It's very, very slim, and that's I think you're referring to the toppings or toppings on composite section, like topping on metal deck. 2 inches is very slim. The basement slab is typically 4 inches. Your garage slab is 5 inches. Garage slab, because it supports some cars and trucks, that's 5 inches. The basement slab is 4 inches. 2 inches is good only for topic, and actually it's not 2 inches, it's 2.5 inches for toppings. But in general, structure slab, the minimum is 6 inches, and it goes to maybe 7 and 8 and 10. But I haven't seen any slab, at least in my career, that is more than that. Otherwise, it would be very heavy slab, and it's not really cost effective. Okay.
Tahir, where you did you ask me a question? Sorry, I'm just having something to eat here.
I was asking you, Gord, because you have been to sites and built some slabs. I'm talking about structure slab, not slab on grade, not
Hmm.
basement slab, not garage slab. I'm talking about structure slab. Okay. What is the kind of range that you've seen? Did you see 16-inch slab thick or 8 inches or 9 inches or 10 inches?
I have seen upwards from 16 to 20 inches up in Fort Saskatchewan.
You work for oil and gas, and you know what? Oil and gas, I told you, those people, they are so rich and they don't care. They put so much factor of safety. But I'm talking about, did you build any residential building that like a residential building, like condo building? What was the slab
Residential, I've not seen anything more than 5 inches, 6 inches.
But again, I think you're referring to slab on grade, like like a basement slab. I'm talking about structure slab that spans not on the soil. It spans between beams.
Oh, like for something without a foundation, just like slab on grade. Yeah, yeah. Yeah, no, those are usually 7, 8 inches, not
I
more
think
than
that
that.
I think that's right. So here is like, here is my input. Structure slab, typically we try to keep it between 10 to 12 inches. That is, even 12 inches is so thick. Okay, as I said, the slab covers the entire area of your building, and you need to save in the slab thickness as much as you can. Okay, and so the typical is going to be 8 inches, 9 inches, not more than that. And so if this is the case, if the most of the cases the slab is going to be 9, 10 inches, let me ask you, how much is the beta in this case? Can anybody tell me how much is the beta if the slab is going to be 200 mil, 225 mil, maximum 250 mil?
42 degrees. Oh,
That's the theta.
beta.
That's
Ah,
the
the
theta. That's the
theta.
angle.
Okay, the
I'm
theta.
asking about the
0.21.
beta.
0.21.
Exactly. So the beta is 21%. And guys, why I'm taking this discussion on a very, very high level, like not really diving deep, because simply in slab, it is very simple. When we go to beams, you will see the discussion will become more complicated. And that's why, to be honest, I prefer to cover this clause in details in beams. And that's not our topic today. Today, we're trying to go through and give you how to design a one-way slab so we can finish our assignment tomorrow. Okay? So please, for now, looks like every slab that the thickness does not exceed 350 mil, then we can use beta as 21% and theta is equal to 42%, 42 degrees. Is everyone clear about that?
Yes.
Yes, that's
Okay.
clear.
Again, as I said, I promise you, I'll give you a deeper, very deep discussion, but not today. That's gonna happen on Monday. I will copy the same two slides to my slides again for beams and go into a deep discussion into the same clause. But for now, to keep going, for slabs less than 350 mil thickness, we use beta as 21%. So once we find the DV, we simply multiply the DV by 21%. So I'm going to skip this one again. Please don't bother by the next slide because this applies to our beams. And you will know why on Monday. But for now, let's skip this one and go to our first numerical example on how to design and check slabs for shear. So I prepared a numerical example, and hopefully this numerical example will put everything in perspective for you, because maybe so far everything is so dry. And let's see if this example will make you feel better about shear design. Let's see. So on the right side, there is a simple plan view, and I'm going to spend some time for you guys to understand the elements on this plan view. And there is some given on the left side. So I'll go first on the plan view. So the plan view, we have beams all around. So we have beams all around my slab. And there is another beam along grid line 3, And this beam along grid line 3, simply it divides the slab plan view into two different slab panels. Hopefully everyone sees that. So if I ask you how many slab panels do we have in this picture, one or two?
2.
Two. You can see them between grid line A and B and 2 and 3, that's one. And between grid line A and B and 3 and 1, there is another slab panel. And remember, when we talk about one way or two ways, we don't think about the entire area of the slab. We think about slab panel by slab panel, one by one. Okay, one by one. So when you think about the slab panel between grid line 1 and 3 and A and B, guess what? Is that one way or two ways? Here is how to think about it. Number one, ask yourself, do we have beams all around? The answer is yes,
Yes.
we do. And because we have beams all around, it means we have beam support for the slab from all sides. it means yes, we need to find our R, rectangularity of the slab panel. Guys, remember how is the rectangularity? Look at the dimensions given to you. Look at the dimensions, and please don't get confused. Every dimension comes with an arrow, and the arrow shows you to where I measure my dimension. So looks like the dimension of the slab panel number 1, it is 7,700. That's center line to center line between grid line A and grid line B, and 3,600 between grid line 1 and 3. 1 and 3. Okay, so you have to estimate the rectangularity, which is always the longer dimension by the shorter dimension. And please pay attention to the following. I'm not talking about the entire area. I'm talking about one slab panel, which means 7,700 divided by 3,600, and this will give you a number that exceeds 2. Once you exceed or equal 2, it means my slab is
One way.
one way. In which direction? Is it in the short or the long direction?
Shorter direction.
Short direction. So please look at my screen and recognize the blue arrow. What is the blue arrow? It is the load path where 100% of the load will go. And because of the symmetry and everything I said applies to panel number 1, it applies also to panel number 2 because it's identical, huh? Same 7,700 divided by 3,600, which means we get a number which is more or equal than 2. Same thing, it means the slab panel number 2 is still a one way in the short direction. Now, once you do that, looks like we can place our design strip. And remember, design strip, it has to cover the load path. And looks like how many design strip do I need? How many design strip do I need?
2.
1.
Jelly, can you tell me why do you need the 2 design strips?
Because you have that 2 shorter distance. So I thought one strip count in one division in one of that. That's why I thought you half of that one whole strip.
No. It's by the way, so you know, not because we have 2 arrows, the 2 blue arrows, it means I have to have 2 design strip. Not really, because you can see if I place only one design strip, it will cover the 2 arrows. So please note that the following, that the number of design strip, it is not the number of the blue arrows. No, one design strip, as Gord said, it will cover the 2 loads. It provides a load path for the 2 blue arrows. Does it make sense?
Yeah, Tahir,
Uh-huh.
I have a question. So let's say if one of the dimensions, you see how they're 3,600 and 3,600, right? From 1
Yes,
to 3.
yes.
Okay, let's say if 1 to 3 was 3,700, it'd be a different design strip, right? Like its own separate design
well,
strip?
at the end of the day, so you can you please mute yourself? So the question was, what if this is not identical, it's not symmetric, and what if I have different R? At the end of the day, Mahdi is what you need to do is you need to cover all the load path. And what does it mean? Let's say that this path carries 70%. Let's say this panel here, it's a 2-way, and this panel is 1-way. So if this panel is 2 ways, it means here we go. I have here a load path going this way. Okay, let's say I'm going to put here 70%, 70%. I'm sorry, 30%, 30%. Okay, and let's say this number here, let's say across this one here, and I will say, let's say this one is 70%. In this case, you will need 2 design strips. One will simply go with the 70 and 100, and the other one will go this way, and this one will simply take care of your 30%. Is that clear?
Yes.
Okay, so at the end of the day, please don't leave any load path that's not covered by design strip. And again, to Jelly, not because I have 2 blue arrows, it means that I do have to have a 2 design strip. No, it's only 1 design strip, and it's continuous 2 spans. Continuous 2 spans. we have here a support point at this point here, and a support point on this beam, and a support point on this beam here. And so my design strip is continuous two spans. But again, this is a later discussion. Later discussion. Now let's go to this side here. And I said here in slabs, please read this one. In slabs, we provide no stirrups. We do not add stirrups to the slab. We add stirrups to beams, okay? And because we don't add any stirrups to my slab, so the shear resistance is provided only by the concrete since there is no stirrup. So the VS will be 0. Later on, which is on Monday, you will see the VR will be the sum of VC plus VS, which is a portion of my shear force will be taken care of by the concrete, and the rest will be carried by the stirrup. Again, don't worry about this one for now. In slabs, we have no stirrups, and that's where the resistance of my shear will be by concrete and concrete only. Now, some other information here. We have SDL, which is superimposed load, is equal to 1 kPa. Live load requirement is 2.4. My concrete is 25 MPa. My concrete cover is for slab is 20 mils. And then my slab has 15 M reinforcement. And then the question is, which that's, by the way, you must understand what is the question. So the question is, check if the slab is safe in shear or not. And remember, there is one information here, and I'm not sure if you guys are paying attention to it. The slab is 150 mil thick. It's over there, huh? The slab is 150 millimeter thick, okay? Now, let me show you on how to check whether the slab is safe or unsafe. Let's do that. So guys, what we do is we do exactly the same thing we've done with this with flexure design. I need to find what is my load. So is that super science? Not really. We go ahead and multiply the slab thickness over there, which is 150 mil. You multiply by gamma concrete, that's 24. And then you add 1. One is what is 1? 1 is your SDL, because whether the SDL or the self weight, both of them, they are dead load. So I need to add to them. And then finally, I'll multiply by 1. Can anybody tell me what is 1? This one here?
Your design strip width.
Thank you, sir. Who said that?
Brody.
Brody, thank you. Guys, remember, don't forget that my design strip, I'll put it here. Don't forget that it's always 1 meter wide. 1 meter wide. That's why the trip width in slabs is equal to 1. Same thing for live load. I go ahead and multiply live load, but the same one, which is the trip width of my design strip, I get 2.4. Now, what the next is, I simply have to go to load combination number 1 and load combo number 2 to find what is my factored load. I've done both of them without repeating myself, and guess what? This number is 9.35. It's more than 6.44. It means load case number 2 governs. And it means going forward, my factored load is 9.35. Okay, so now we can see that's a cross section through my design strip. And as we agree, this one is continuous two spans. Why is that? Because we have here one support, we have here one support, and we have a third support here. So you can see my design strip, which I'll draw it for you. So my design strip is here. This is my design strip that is supported by, I'll give it a color. I'll give it a color here. So let's say yellow. So my design strip in yellow is supported at 3 different points, 2 spans. Guys, how do we find the bending moment and the shear for continuous slab?
Monolithic diagram.
Let me ask you, do we use WL over 2, same as we do with the simple beam?
No.
Or WL like for cantilever?
No.
No. I need everybody, guys, to just confirm that you guys are following. Whenever you see continuous beam, don't use the simple beam equation for shear or bending. Don't use the cantilever equation for beam for bending and shear. Instead, you guys know continuous beam, the code has some simplified approximate design aid, which is the table. Again, for the sake of time, I didn't give you the entire table. I just only copy the one that you're going to use. You guys remember this picture? Have you seen this picture before?
Yeah.
So this picture, what it helps you to find the bending moment and the shear for continuous beam or one-way slab. Here, the only difference is when we design for bending, we took these numbers. Look at these. These are the numbers that we used for bending design. So we have five different numbers, right? How about for shear? Where can I get the shear? Do you see anywhere on my screen where can I get the shear value?
Yes.
Is it the
At
I
the
number
boxed
right
it.
at the
I
top?
boxed
WL
it. I boxed it already
WLN
on
over
my
2.
screen. I boxed it already on my screen, and this number, guys, this is the shear value. The shear value, it is 1.15 multiplied by W multiplied by L sub N divided by 2, which is, when you think about it, you will see, you know what? This is very similar to my simple beam reaction, because simple beam reaction is how much? What is the reaction for simple beam?
For simple beam, R over 2.
It is R, and the R is equal to WN over 2. So you take the uniform load, you multiply it by the span, and then you divide by 2 because we have two supports. That's why the reaction is equal to WL
Yeah,
or
over 2.
multiplied by, excuse me?
WL over 2.
Yes. And the difference is we have only multiplied by 1.15. It means my shear force here gets a 15% more because of the continuity of the slab. When the slab is continuous, it adds more reaction on the intermediate support. Okay? So that's very simple. Really, my reaction is 1.15 multiplied by W, which is my factored load, multiplied by the clear span divided by 2. Very, very simple. And please don't get confused. It is not square. The span here for the moment is squared. For the shear force is not squared. Okay, so let's see. But guys, remember that we do not really get those numbers right away. What do we have to do is, it's here. Conditions need to be checked prior to use the table. Excuse me. So there are some conditions we have to check before we use our table. Please don't jump right away and use the table. You need to provide the condition, which is 1, 2, 3, and 4, and 4 conditions. Number 1, it's prismatic, which is always happening all the time because we're not changing the thickness of my slab. Number 2, do we have uniform load? Yes, we do. And then you say my factored live load. I'm gonna zoom in. My factored live load, so 1.5 multiplied by my live load, and then divided by factored dead load. Where did I get the 2.4 and 4.6? Please look up. You can see here is my 4.6 and 2.4. So you just have to do the check. It's 63%. Anywhere less than 2, it's okay. So it means this condition is okay. How about the spans? Do we have equal spans? Please look up my screen. Do we have equal spans?
Yes.
Yes, we do. So we have equal span, exactly equal, but also the code allows you to have extra 20%. So this, guys, this problem, you can still find the shear force and the bending moment, even though the span is not equal. We have allowance of 20%. Guys, can somebody help me with 20% of 3.3 meter? I need some help. What is the 20% of 3.3? I guess it's 60,
0.66. 0.66.
yeah, 66 centimeter, right? So
Yeah.
guess what? Guess what? It means I can use the diagram if it's 3,300 and 3,300. Even this number is not 3,300. Is 3 I'm on 3,960. We can still use the diagram. If you add 660 mil to this span, we can still use the diagram. Why? Because the span increased by 20% maximum. I can still use the diagram. Anyway, for our case here, it is exactly equal. It means I don't have to worry about this one. But remember, the code allows 20% of increase. Guys, finally, if those conditions, all of them, they are met, it means I can find my VF How much? Very simple. It is 1.15, which is over there, multiplied by W factor. Where W factor is, it's over there. Huh? It is 9.35 multiplied by the span, which is 3.3 meter, divided by 2. And remember, it is clear span. Please look at my picture. There is some dimension between grid lines, which is 3600. But given that the beam width is 300, it means at the end of the day, my clear span is only 3300. Now I need to remind you, actually I have a mistake on my side. I should have added some labels here to show the dimension of my beam, because you cannot do that, huh? Maybe myself on my Revit, I can find the clear dimension, but for you guys, I need to write here that the beam width is 300 millimeters. I'll do that and re-upload. So let me take a note, please. At slide 9. So guys, please take a note that all beam width is 300 mil. And that's why when you look at my cross section here, I'm able to find what is my clear span, and the clear span is what you use to find the shear. What does it mean, guys? It means my factor, the shear force on my slab is 17.74 kilonewton. Now, is my slab safe or unsafe? Can I tell this right now? Can I say right now, without any further calculation, can I tell whether my slab is safe or unsafe? Yes or no?
For now, no. What is your VR?
Exactly. Thank you so much, Jelly. At this point of time, we know how much shear affecting my section, but we don't know how much my section can take. And that's what I will do in the next slide. Is that clear, guys?
Yes, that's clear.
Okay, so let's move on to the last part, and you will see it's super easy. So what Tahir will do is, now it's time to find slab shear capacity. And remember, shear capacity here, since we have no stirrup, it is provided by concrete and concrete only. And that's why VR is equal to VC. There is no VS for the stirrup. And how much? Very simple, same as the equation I gave to you early today, which is phi C multiplied by lambda multiplied by F prime C multiplied by beta by dV by B. Now let's go one by one. Again, don't get so excited about it. It's very easy. Let's go one by one. You guys know that in order for us to find our dV from the code, it is the greater of 90% of D or 72% of H. So looks like H is how much? Can anybody tell me how much is H?
900.
Jelly, we're not talking about the beams that we covered today, this morning, like, early. No, we cover slab. So H here is the slab thickness.
Okay. Sorry.
You're still stuck somewhere on slide number 1 or 2.
Okay.
Okay, so the slab, we're talking about slab, not beams. So the slab here, it is 150 millimeter thick, which means H is 150. And you can see here from the H, I subtract the cover and then subtract also half bar. Okay, where is the stirrup? Because in beams, when we estimate the effective depth, we also add here 1 thickness of the stirrup. Remember, in slabs, we have no stirrups. And that's why the G is equal to H minus concrete cover and then plus half bar. Okay, where is the... You can see in my input over there, I said the slab is reinforced with 15 M bars. It's over there, huh? That's the bar diameter. So now we know the D, and once you know the D, you can take the D into this equation, and D is 122.5. So we have to do the math, and please, I need somebody to check me.
You got it right.
Okay, so the dV is the greater of 90% of D or 72% of H. So we got 110.25 mils. Great. What's next? So guys, as I made it very simple. According to 11.3.6.2a, the beta is equal to 21%. Where Tahir got that, let me remind you, it is over there. So in the code, it says whenever you have a slab that is not greater than 350 mil in thickness, then we can use the beta is equal to 21%. Remember, It's 11, 0.3, 0.6, 0.2, item A. So this clause here, it tells you use beta equal to 21%. Now I know that beta is 21%. So guess what? I'm ready because everything is ready. Please try to repeat after me. Phi C is equal to 0.65%. Always. Lambda is equal to 1 always. My F prime C, it depends on concrete that goes into the slab, 25 MPa. And then my beta is equal to 21%. And this number is my D sub V. And then finally, 1,000. What is 1,000? Can anybody tell me what is 1,000? I think Brody will say it.
Strip, design strip.
Yeah, that's the width of your beam. That's the width of your design strip. Because remember the equation, it is phi C lambda F prime C square root beta dV multiplied by the width of your beam or design strip width. So what you get at the end, guys, I need all of you guys to do it right now. Please do this. Please do this. Find for me this number. Please do it on your calculator, please. Any good news? Any good news?
Well, I got the same answer as you did.
But the thing is, what you get, I bet you, it's a bigger, it's multiplied by 1,000, huh? And that's why I ask everyone to do it. The number you will get is, you will get a number which is in Newton, because everything on the left side is in Newton and millimeter. So when we multiply everything in millimeter, for example, the B is equal to 1,000 millimeter, the D sub V is millimeter, and F prime C here is Newton per millimeter square. What happened is, when you get your V sub R, which is the shear capacity of your slab, this number is in Newton. So please take a note that my number here, I did the conversion and I divided by 1,000 to turn my Newton into kilonewton. Guys, at the end of the day, what happened is my slab capacity in shear is equal to 75. What does it mean? It means my slab can resist in shear up to 75.25 kilonewton. Are we safe or unsafe?
Safe.
It is on my screen. This number way exceeds the 17.74, which is your VF. So the slab, in fact, the force acting on the slab is only 17.74, while it can take all the way to 75. It means it is safe. It is safe. Okay? Now let me ask you, what happens if the opposite happened? What happens if you found out that your VF exceeds your VR? Exactly here, huh? What happens if your VF exceeds your VR? What does it tell you? It means the applied force, the applied shear force, exceeds the capacity, shear capacity of your slab or beam. What do you think? This
That
is
means it's
unsafe in shear. And what do you propose? This is if you encounter this condition, if you're estimating all the numbers and your VF happens to be more than VR, look at this. There are two solutions. Number one is increase the thickness of your slab. Number two, increase concrete compressive strength. And why did Tahir came up with those solutions? Look at the equation. Can I ask you, does this number change?
no.
Does this number change?
No.
No, that's lambda, that's 1. Okay, but if I bump up my concrete strength, guess what? If this number goes to 30, what happens to your VR?
It will increase.
Increase, correct. And what if I increase my H of the slab, the thickness of the slab from 150 to 175? What happens to your D sub V? What do you think?
That will increase
Because
too.
when I increase my H, both the H increases and the D increases. And you can see the DV is over there. So the DV is connected to my D and my H. So whenever I increase the H, I'm increasing the D and I'm increasing my DV. So increasing the slab thickness will also help. How about the 1000? Let me ask you, this 1000 here, does it change?
It doesn't change anything.
Doesn't change. Always your design strip is 1 meter wide, which means we're not going to change our design strip. Huh? So finally, here is the answer. The answer is if you run into a problem in your shear design, the answer is increase the slab thickness. That's number one. Or option number two is increase concrete compressive strength. But guys, this discussion applies to slabs because we have no other option. In beams, we have a third option, and the third option is, anybody help me to put the third option for beams?
You have to put an extra rebars on top.
No, you know, the other option for beams is add stirrups, which is not available for slabs because we do not add stirrups in slab. Okay, and that's a discussion on Monday. So for slabs, we have only two options. For beams, we have three options, which is adding stirrups. Is everyone following?
Yep.
Okay, guys, here is my plan. Today is a long day for me, but it's okay. After 4 o'clock, I will simply release my assignment number 5, which is one-way slab design. Tonight, I will release assignment number 5, which is one-way slab design for bending and for shear. And you can see we finish the one-way slab design in bending and shear, which means we're able to do it. And in tomorrow's class, please get all your notes for one-way slab flexure and shear design, and you guys will solve the assignment in the class time tomorrow between 1 and 3. There is no new material in tomorrow's class. I'm gonna help you guys. You will work, you ask me question, and hopefully at the end of 2 hours, you're able to finish the assignment, which means no extra effort for you outside the class. And I know some of you, I say, you know what, I will be busy. You know what, I have so many exams on Friday. I'm gonna use the class time because Tahir is not teaching anything. Let's use the class time. Don't attend. Please don't do that. I'm trying to help you out. I will be with you guys. You solve your assignment, you know, get out of your way and submit it if you're able to finish in 2 hours. Do we have a plan for tomorrow, guys?
Yes, and we appreciate that a lot, Tar.
Okay, thank you so much, and I'll see you guys in 20 minutes from now. Thank you, and have a good day.
Thank you,
Tahar, quick question.
Oh, sure, go ahead.
So the assignment's not due tomorrow, though, right? We're just
No,
gonna be.
no. The assignment will still, as I promised, the assignment is 1 week from I publish it.
Okay.
So the due time is still the same. I'm trying to avoid you guys by yourself in your room, by yourself on the assignment. I'm gonna give you 2 hours to solve the assignment in class.
Thank you.
No problem. I'll see you guys in a few minutes in other class. Thank you.